Good morning. Today's lecture is going to be a review of something that is called polarity, specifically molecular polarity that you see at the top here of this whiteboard presentation. Molecular polarity, again, we're looking at compounds that are covalently bonded, so we are sharing electrons. And this again occurs when we have a nonmetal bonded to another nonmetal. Okay, we're now looking at ionic compounds. Ionic compounds are held together by charged particles. Those are called electrostatic forces. Molecular polarity is looking at a covalently bonded group of atoms. And because you're sharing electrons, the misconception for some students is how can the molecule be polar? Now, when I mean polar, that means a molecule will have a positive end and a negative end. How is that possible when you're sharing electrons? Well, if you're not sharing the electrons equally, you're going to have a difference in the pull on the electrons, and therefore the more electronegative atom will pull the electrons towards it more often because of the difference in electronegativity. It's Coulombic attraction, and therefore will develop a negative end and a positive end of these molecules. Now, they're not full positive one and negative one like ionic compounds. They're actually partial. So a lot of times you'll see this little Greek letter, and that letter symbolizes a partial positive negative end. But we still treat it like it would be a negative or positive like an ionic compound. It's just not as big of a negative and positive difference. Okay? So because there's a partial negative end and partial positive end, just like ionic compounds, molecules can attract to other molecules. And that leads us into eventually in this unit towards the end, a review of intermolecular forces. Okay? Now, to look at molecular polarity, the first thing you have to do is review a little bit on bond polarity. Bond polarity is looking at the bonds themselves, the parts that make up the whole molecule. There are two types of bonds when it looks at covalent bonds. One is a nonpolar covalent bond and a polar bond. A nonpolar bond only occurs when we have equal electronegativities. The only way we can have that is when it is bonded to itself, because that's the only way we can guarantee that the two atoms in the bond have equal electronegativities. Therefore, they share the electrons equally. Great example of that is hydrogen. Here I've shown hydrogen with its 1s orbitals in which they overlap. This shaded region right in here of the overlap is where the bond occurs, and the electrons are possessed in that area of where the two orbitals overlap. Those electrons are shared between each hydrogen equally, and this is a nonpolar bond. So the only way you can have a nonpolar bond is if it's bonded to itself. If you have a molecule that has more than two atoms, it is more than likely going to be between different elements, and therefore all other bonds are considered polar bonds. Because if it's two different elements forming a covalent bond, they are going to share unequally because every atom has a different electronegativity. Now, there's different disparities. Now, I've seen before on the national exam questions like, which bond is more polar? Well, again, you have to remember which element is the most electronegative. I'm hoping you answered that with fluorine. So the farther you get away from fluorine, the more electronegative that atom is going to be. Don't forget the noble gases do not have electronegativity values or very small ones because of the fact they have full shells. Electronegativity is the pulling or the gaining of electrons towards electron affinity. Fluorine is the most electronegative atom. It's the farther you get away from it. So the farther the two atoms are from each other, the more electronegative that bond will be. If it becomes so electronegative differences, we don't have a covalent bond, we actually have an ionic bond. Okay, so HCl, okay, chlorine is more electronegative than hydrogen. We show that difference by putting an arrow pointing to the more electronegative atom. This arrow is called a dipole because it points to the more electronegative atom, meaning that in this molecule, the chlorine end will have a partial negative and the hydrogen will have a partial positive. Hydrogen, fluorine, same thing. However, the difference between these is even greater because fluorine is has even more separation, and we know fluorine is the most electronegative atom. So this arrow would be even longer because we know fluorine is the most electronegative atom. It has a greater or larger dipole, which means it's going to be more polar. So the HF molecule is more polar than the HCl molecule. Now that's looking at just molecules that possess one single bond. So if you have a diatomic molecule, two atoms, if it's the same atom bonded to itself, it's a nonpolar molecule and it's a nonpolar bond. If it's a bond formed between two different nonmetals, then it's going to be a polar bond. The farther they are away from each other, the more polar the bond is, and the more polar the molecule is. Okay? Now what happens when you have a central atom where you have more than one atom coming off the central atom? Now we have to look at symmetry arguments. Okay? First thing you have to have is you have to have polar bonds. And for the most part you will, because if you have more than one atom bonded to itself, more than one bonds, more likely it's not going to be bonded to itself. Most of those molecules are going to be diatomic. If you have a central atom, usually the atoms coming off are different, and therefore the bonds are going to be polar. Then the question becomes, to have a polar molecule, is it an asymmetric shape? To be a polar molecule, you must have an asymmetric shape. Okay? So a polar molecule will have an asymmetric shape. A nonpolar molecule will have a symmetric shape. Okay? So to have an asymmetric shape, you've got to have one of these two criteria. Either the central atom must have lone pairs on them, lone pairs of electrons, would be an asymmetric shape, and therefore would be a polar molecule, or it has to be bonded to different atoms, different terminal atoms. Okay? So if I have an atom bonded, let's say in this situation, the central atom carbon is bonded to a hydrogen and a nitrogen. If it's bonded to two different terminal atoms, this would be an asymmetric shape and therefore a polar molecule. Okay? Let's take this a step further. So a polar molecule, on the national exam, the type of verbiage they use is a polar molecule has a dipole moment. Dipole moment meaning that when we add the dipoles of all the bonds together, they result in a dipole moment or an overall dipole. A nonpolar molecule has a zero dipole moment, which means the dipoles all, because of their symmetry, all cancel each other out. Here's a quick little visual vector addition. I know some of you in your math classes, I think, got to vector addition. Hopefully you did. If not, this is just a quick rundown of that. Let's say you have two dipoles. One has got 3 units to the right, and the other one has 2 units to the right. Because they're both pointing in the same direction, when we add the vectors together, it adds up to an overall vector that is 5 units large. Because it is a resultant, because it does result in an overall vector of 5 units, it's said to have a dipole moment. So anything with a dipole moment means that the dipoles themselves do not cancel each other out. They actually add to an overall vector, which is called the resultant vector. And the verbiage we use on the national exam is a dipole moment. In the second scenario, we have two vectors, but they're in opposite directions. 3 units to the right, 3 units to the left. When we add them together, they, in essence, kill each other. They cancel each other out, and we're left with no resultant vector, 0 units left. That is an example of a symmetric molecule in which the dipoles cancel each other out, and the molecule is said to have a 0 dipole moment. Therefore, it will be a nonpolar molecule. The greater the dipole moment, the bigger the dipole moment, the larger the resultant vector, the more polar the molecule is. Okay? So, let's look at how this symmetry argument lines up. Here is carbon tetrafluoride. Each carbon F bond is a polar bond. It is between two different elements, and fluorine is much more electronegative than carbon. So this is a very largely polar bond, which has a dipole pointing to the F. Well, if I draw carbon tetrafluoride, CF4, we get this shape, which we should know from our last lecture that this is a tetrahedral shape, and the bond angle is all 109.5 degrees. The fluorines are all separated by 109.5. No matter which F's we look at, they're all separated by 109.5 degrees. If I draw in the dipoles, every bond is pointing to the F. And because they are between the same atoms, they are all the same size because each dipole is of the same effective difference in electronegativity. And they're all poling equally at 109.5 degrees. And because of that, just like this situation up here, because they're all pulling away from the carbon at equal angles and at equal size, they end up canceling each other out. Therefore, this molecule has a zero dipole moment, and because of that, it is a nonpolar molecule. So even though this molecule has extremely polar bonds, because of symmetry arguments, they cancel each other out, and the overall molecule is said to be nonpolar. And then that plies into why carbon tetrafluoride is such a low boiling point, is because of that symmetry, and because it has a zero dipole moment, it does not really attract to itself very well because it doesn't have a negative pole and a positive pole for it to attract, and that'll lead us into intermolecular forces. Let's turn the page. Now, some examples are not as easy as you would predict. Okay, CH2F2. If you look at this molecule right here, I drew the Lewis structure. Now, oftentimes they'll draw the Lewis structure for you, and they'll say, "Is this molecule polar?" They purposely do this to you because if I look at this structure, you think, okay, this arrow points this way and this arrow points this way. Between the carbon and hydrogen bond, believe it or not, carbon is more electronegative, points to carbon, points to carbon. Students think that this molecule is perfectly symmetric, but it's not. Why? Because a Lewis structure does not tell us the true picture. We have to draw the VSEPR structure, and when we do draw the VSEPR structure, you'll notice that the fluorines are not directly across from each other. They are off at angles. So if I look at these two arrows, they will not cancel each other out, and the hydrogen-carbon bond will point to the carbon. So I look at all these bonds based on how they're pointing. Okay, if I were to add all these vectors together, we would end up with a resultant vector that would probably be pulling or going in this direction between the two fluorines. So this molecule, therefore, does have a dipole moment because the individual dipoles are not effectively across from each other, canceling each other out. Therefore, this end of the molecule would have a negative end, and between the hydrogens would have a positive end. So this would be an example of a polar molecule. So don't let the Lewis structure confuse you. You have to draw the VSEPR structure and see, are those arrows, those dipoles of each of the bonds, are they effectively canceling each other out, yes or no? So the general rule, if all of the atoms come off the central atom, if they're not all exactly the same, usually the molecule is going to be a polar molecule. Water, same thing. If you look at the Lewis structure, you think the hydrogens, because they're both pointing to the more electronegative action, would cancel each other out. But again, we have to draw the actual VSEPR structure. Water, just like CH2F2, has got a 109.5 degree geometry because it has 4 electron domains, just like the one above. So we have a 109.5 degree bond angle between the two hydrogens. However, the shape above is called tetrahedral because it's 4 bonds. The electron domains are all a bond. Down here, the geometric shape is bent. Again, even though we have a tetrahedral overall shape, the name of the molecule is bent because not all of the electron domains are bonds. Again, if I look at the arrows, you'll notice that the arrows are all pointing, they're not pointing directly at each other, they do not cancel each other out. And if I add up these two vectors together, they add up to an overall vector that is pointing between them in this direction. So water, between the two lone pairs, is where the negative pole is, and between the two hydrogens is the positive pole. Water has a dipole moment. It is a polar molecule, and therefore water does have strong IMFs for each other, which we should know from last year. A couple other hard arguments to look at. Xenon tetrafluoride. Here's an example of a hypervalent molecule. When we draw the Lewis structure, this has got 6 electron domains. And if you remember, the two lone pairs of electrons must be opposite to each other because they possess the most or largest area. So they have to go into the large bond angle. Well, whenever you have 6 electron domains, all the bond angles are 90 degrees. It's an octahedral shape, but you must put them opposite each other, which means then we put the fluorines So here again, students would think, okay, there's lone pairs on the central atom. If there's lone pairs on the central atom, like we talked about last year, if there's any number of lone pairs, it has to be a polar molecule. Usually, yes. Here's an example of an exception. Why? Because the lone pairs are opposite each other, they effectively do cancel each other out. Last year, whenever we had any lone pairs, they were never all directly across from each other. So a couple of these new shapes that we get from the new ones, specifically when we have 5 electron domains, the linear, where we have a 2, 3, okay, where we have 2 bonded atoms and 3 lone pairs, and this shape, this 4-2 shape. When we have these two shapes, because the 2 lone pairs, or the 3, are opposite each other, they cancel each other out. This molecule has a perfect symmetrical shape. So just because it has lone pairs doesn't necessarily mean that it will be polar. You do have to draw it. Okay, water, the lone pairs are not exactly across from each other. They will not cancel each other out. But whenever they are, in this case, this shape, so whenever we have a square planar shape, as long as all the atoms coming off are the same, it will be a nonpolar molecule. It has a 0 dipole moment. 2, 3, there's an example of that in the previous packet lecture that I went over. Okay, in that molecule, you have the 3 lone pairs, or the disk of the material. They're all 120 degrees around. They all cancel each other out, but then we have an atom on the top and the bottom. As long as those 2 atoms are the same, this also is a symmetric shape. So you have to be careful. If you have lone pairs, it doesn't necessarily mean that the molecule is polar. Most often than not, it will be, but you might want to draw the molecule and ask yourself, are they directly across from each other, yes or no? Lastly, what happens when you're bonded to itself? Ozone is the classic example here. You would think because it's bonded to itself that this would be a nonpolar molecule, but it isn't. Ozone is polar. Why? Here the lone pairs come into question. When I actually draw the VSEPR structure, you'll notice that the lone pairs do make for the bent shape. The bent shape is an asymmetric shape, and therefore there isn't, while there isn't all these differences in electronegativities, there isn't another lone pair to cancel out the lone pair off to the top. So this molecule does have an overall dipole moment. So this page, just going over examples where last year I gave generalizations that always fit the mold. Sometimes in AP that's not always the case. These are the classic examples of things to watch out for. So when I go back to the previous page where I say, are there any lone pairs? Usually it's asymmetric. Are all the atoms coming off the same? Okay, if they're not, then it's usually asymmetric. When in doubt, draw it, and be careful of a couple of these exceptions. This is why it's really important for the homework to go through them, go through those tables. All you've got to do in the table now is, after you've drawn the Lewis structures, is tell me, is the molecule polar or nonpolar, and mark that down. And then if you have any questions, if something doesn't match up with what you placed down, please give me a shout out, and I'll be glad to get back to you and see if you have a misconception, or if maybe I even made a mistake myself. All right, good luck. I'm hoping everything's safe with you at home. Keep working, and we'll keep pushing the national exam. Try to do a little bit every day. Thanks again for listening.